here. Right, so a new chapter, and this chapter is on chemical equilibrium. Okay, so do you guys know what equilibrium means? Okay. So let me give you two types of reactions here. Okay, first reaction one, we'll have reactants A plus B go to products C and D. Okay, so that's one reaction. And let me give you another reaction. Okay, so reaction A plus B, reactants A plus B go to products C plus D. So what's the difference between these two reactions? Anyone want to tell me? What's the difference between this one and this one? Same reactants, same products, but what's the difference? Okay. Difference? The arrows, yeah, correct. So this one is a reaction that we're going to call it an equilibrium reaction. So this one here at the bottom is an equilibrium. Okay, this reaction up top is a reaction that goes to 100% completion. So at the end of the day, at the end of the hour, at the end of whatever time period, this will have product C plus D. Here, it's a quite different scenario. Here we will have a little bit of A and a little bit of B reactants left over. To what extent does this reaction go to 50% completion or 75% completion or 10%? To the extent that you have A and B left over. Okay, how much A and B reactants do you have left over? Because this reaction does not go to 100% completion. To the extent that this reaction goes in the forward direction, that extent we're going to call the equilibrium constant K. Okay, so that's an important point of this chapter, K. Okay? Okay, notice that this is capital K. Capital K. Okay, so this K is going to be called the equilibrium constant. Okay. And a couple of things about K that I want you to realize. This is not lowercase k. Okay? Lowercase k was called the rate constant. Okay, capital K is the equilibrium constant. And this capital K is going to equal to the products, concentration of the products, raised to the coefficient. You know we balance an equation, right? You know how to balance equations? Yes? Okay. From Chem 1. So raised to the power of whatever the number is in front to balance it. Concentration of products raised to the power of whatever number is in front of it to balance, divided by the concentration of reactants. Okay, concentration of the reactants to the power of whatever number is in front of it. This is called the stoichiometric coefficient. Okay, divided by the concentration of reactants. Okay, raised to the power of whatever number is in front of it to balance it. Okay, this SC that you see here is called the stoichiometric coefficient. Okay, the number that you put in to balance it. It's raised to the power of that number. Okay, so what do we do in this chapter? What do we do, not just in this chapter, okay? What do we do since chapter 1? Okay, we always balance our equations, okay? We balance it and that number becomes the exponent. Okay, this is products over reactants. All right, so very important rules here, okay? Super important rules. The first important rule, number 1, okay? Everyone knows this rule, okay? No solids, no liquids go in here, okay? Absolutely no solids, no liquids. You just completely omit. Okay, so no solids, no liquids. Let's put that down here in this K, capital K, which is the equilibrium constant. Okay, no solids or liquids go in here. absolutely no solids or no liquids go in the equilibrium constant K. Okay, no solids, no liquids. So if you see a solid in here, does it go in this K? Yes or no? Okay, now if you see a liquid in here, does it go in this K? Okay, you just ignore it. You pretend it's not there. It's there, but it doesn't go in here. Okay, it does not go in here. Okay, you may wonder why no solids, because number one, solids do not have a concentration. Okay, solids have a density. That's why we don't do solids. We don't put solids in there, because solids don't have moles over liter. Okay, and then the reasons why we don't have liquids is because liquids is the solvent. Okay, the reaction takes place in the solvent, usually water. Okay, is the solvent. So the reaction happens just like in your body. Everything happens inside your blood. Okay, but the blood is not part of the reaction. It's just a medium in which the reaction happens. Okay, your liquid is the medium in which the reactions happen. So we don't include that because they do not participate. They do not participate in the reaction. Go ahead. Yes, sir.
What was it for the equilibrium constant? It was what over reactants?
Products over reactants. Okay, very important point to remember. And what goes not in here? Do not put solids and liquids. Do not go in here, right? Okay. If you want to know the reasoning, solids don't have a concentration, and liquids is the medium. Okay, liquid reaction happens in the liquid. All right, so that's point number one. So let's repeat it again because I've seen, miss easy points. They put solids or liquids in here. You don't do that. No solids or liquids in this expression. Okay, rule number 2 here is that this K is unitless. Okay, unitless. What does that mean? Okay, it means there are no units in this products over reactants. Okay, no units. Rule number 3, just like vapor pressure and just like rate constant K, this is quoted at a specific temperature. There are 2 other things that were quoted at a specific temperature, if you remember, from chapter 11. That was vapor pressure, okay, at the very beginning of the class, and then also last chapter, rate constant K. Okay, so these 2 things, and now this one also is quoted at a specific temperature. You change the temperature, you change K. Change equilibrium constant K. Alright, so these are the 3 things I want you to know about the equilibrium constant. It's capital K. Capital K. Okay, and what are these C's and D's to the power of? What are these? The number, yep, the coefficient. Correct. Very good. Good job. Alright, now let's talk a little bit about K. Let's say we have K is greater than 1. What's this? Let's say us do K is equal less than 1. If this K products over reactants equals 1, and this K is greater than 1. Okay, so remember, this is, Alex, just for everyone here in the class, products, don't forget to raise it to the power of the coefficient divided by the reactants. Okay, each reactant raised to the power of its own coefficient. Okay, what happens if you do calculate this in your homework and you get a value of K which is unitless and it's less than 1? Okay? If you get a value of K that's less than 1, that means you're going to have more reactants than products. Okay, so the reaction's probably going to go this way. We have more reactants. this is reactants. Okay. So the reactants are favored. More reactants than products. If this K, if you plug in the concentration for the products, raise it to the power, divided by the concentration of the reactants, raise them each to their power, and it's really large, products over reactants, this ratio is really large. Okay, this reaction is moving forward. Okay, so it's like this. So this is a situation where the products are favored. You'll have more products than reactants. Okay, and if you do the products over reactants, each raised to their power, their coefficient, and it equals 1, then neither is favored. Okay, so when this reaction is all said and done and completed and finished, you'll have an equal amount of products and an equal amount of reactants. So neither is favored when this K, capital K, is equal to 1. So there you have it. Okay, so the most important part of this, class, of this chapter, is stated here. Oh well. What can I do? All right, let's do some examples here. Is this reaction at equilibrium? The answer is yes. So if it's at an equilibrium, do solids go in here? No. Liquids go in here? No. What are the only things that can go in here? Okay, gases and aqueous. Okay, remember aqueous from Chem 1? Those that are dissolved in water. So what would the equilibrium constant for this be? Okay, the concentration of O3 raised to what power? 2 divided by the concentration of O2 raised to what power? 3. Okay, everyone see that? Okay, what happened if these were gases? O2 is a gas. O3 is a gas. Okay, if they were gases, we can do K. We can put something like Kp. P is for pressure. It doesn't matter. We can also express this, if these are gases, as the pressure of O3. Okay, squared divided by the pressure of O2 cubed. So this happens if you're dealing with gases. Gases. Okay, you can express it in terms of pressure. How about this one here? Okay, what would the equilibrium expression for this one be? Okay. This EQ stands for equilibrium, and let's do it in terms of concentration. What would it be? The concentration of ammonia, which is NH3, raised to what power? 2 products over reactants divided by the concentration of N2 raised to what power? 1 times the concentration of, what else? H2 raised to what power? 3. If there's a solid or liquid in here, are we going to put it in? No, we just ignore it. Right, so as with everything, make sure you're balanced. Shall we do one more here? How about this one? Do this one here. Okay, what would the K, I'll do KC here. KC stands for concentration. Okay, products over reactants. So the concentration here, C for concentration. Is this balanced? It is. Concentration of SO3 divided by products over reactants. Concentration of SO2 raised to what power? 1 times concentration of O2 raised to what power? 1/2. Okay. We can also do pressure because let's say these are gases. If these are gases, we'll do the exact same thing except we will do pressure. The P here stands for pressure. Right, the mistakes I see here is that people put solids or liquids inside here. Are we going to put solids and liquids in here? No. Okay, do these have units? Okay, does K have units? The answer is no. No units, no solids and liquids. Okay. And it's products over reactants. That's how it is. Right, here's another one. Is this reaction at equilibrium? Yes, it's at equilibrium. So the equilibrium constant for this reaction is, if you look at the next page, is 4.63 times 10 to the minus 3. Okay, that's the equilibrium constant at 25 degrees. Okay, for this reaction, I'll rewrite it from the previous page. N2O4 going to NO2. Okay, looking at the value of this number. Okay, just looking at the value of this number. When this reaction is complete, will we have more products or more reactants? What is more favored? 4.63 times 10 to the minus 3. Okay, we would have more reactants or products. 4.63 times 10 to the minus 3. It would be reactants. Okay, we favor more reactants. Okay, we'd have products, you're right. We will have products, but which will we have more of? We'll have more reactants. Okay, why is that? Okay, this value is less than 1. Okay, so this one is an equilibrium that favors reactants. You'll have products, you're right, but more reactants than products. Okay, why does it favor reactants as opposed to products? Again, look at the magnitude of K, it's less than 1. How about if I give you this example? If I gave you $1 million, okay, if I gave you $1 million, would you move forward or backward in your life? Okay, most people would move forward. Okay, so if $1 million is a lot, $1 million is a ton of money. So a large K value, like $1 million, the reaction is moving forward. Okay, so the larger this is, the more it's moving forward. Okay, you have to remember this is products over reactants. Okay, raised to the power of its coefficient. All right, so yes, this one is going to favor reactants because the number is less than 1. So this is something we want to know. Okay. And this kind of tells us the same thing here. Right, think of a seesaw. Okay, this is a seesaw. In an equilibrium reaction, okay, it's never going to go to 100% products. Okay, it'll be maybe like this, maybe like this, maybe like this, maybe like this, like this, like this. Okay, who knows? Whatever it is, we will have some distribution. Okay, reactants and products. Okay, and if K equals 1, you have 50-50. Okay, right here. Check your arrows also, right? Check your arrows. Okay, you see those 2 arrows? Okay, like this. Okay, you have to think of equilibrium reaction. Here. All right, for gases, we have something here. So let's just go over some K's for now. Okay, so we have, let me just see, note on K's. So we have a Kp, the P stands for pressure. You have a Kc, the C can stand for concentration. There could be a K equilibrium, okay? Later on in this course, we'll be talking about Ksp. So that's chapter 16 or so. So this stands for solubility product constant. Okay, there's a Kw. That W stands for water. Yes, water is in an equilibrium with acid and base. Okay. So there's a whole different bunch of Ks. Okay, there's something that we will not talk about, Kf, which is formation of complex ions. So there's a whole bunch of different Ks. Okay, so the subscripts are important, but all of these Ks just basically mean the same thing. And what is that meaning? Products over reactants. Okay, raised to the power of the coefficient. And that's what K means. And you don't have to worry about the subscript. They just make, they're very specific for a very specific type of reaction. Like this one is for water. Okay, this one's for a complex ion, which we will not talk about in this class. Okay, so don't worry about the subscripts, but they do have a very specific meaning that they convey. As an example of that, okay, we have a conversion of Kp, or we have what Kp equals in terms of Kc. So Kp is the equilibrium constant in terms of pressure. And Kc is the equilibrium concentration in terms of concentration, equilibrium. Okay, so going from Kp to Kc. Okay, this happens if you're dealing with gases. I'll give you this on the exam, so you do not have to worry about memorizing it, okay? So I don't think, unless I tell you to, don't memorize it. This, do not memorize. Okay, T is the temperature. Okay, R is the constant, which is 0.0821. Okay, and delta N is moles of gas final minus moles of gas initial. That's the exponent here. Again, you do not have to memorize it. It will just be plug and play. Moles of gas final. So this is just going from Kp to Kc. Okay? P is for pressure, C is for concentration. What are we talking about here? What state? Gases. Okay? This is for gases. This is for gases. Right, a whole bunch of K's that we'll talk about. We'll teach you this later on. We'll find out about this later on. Okay? So yeah. Okay, what's the equilibrium constant for this reaction? First of all, is it an equilibrium reaction? Yes or no? Okay, the answer is yes. And what would it be? Let's do it in terms of concentration C. Okay, what does that solid mean? Ignore it. What does this solid mean? Ignore it. And so what is the equation? Products over reactants. So this would be the concentration of CO2. Any exponent in front of it? Or raised to any power, I should say? No, it's balanced. Okay, this is a gas, so we can also do it in terms of pressure P. Right. So what was different between this and the previous ones? What did we ignore? Yes, yes, sir. We ignored the solid. Okay, so you just don't ignore it, as you mentioned. Yes, correct. Okay, so these are the two equilibrium constant, one in terms of concentration, the other in terms of pressure. Okay. And here you go. Okay, so don't do this on any quiz or exam. You can get some points off. All right, I see this a lot. And it's also an easy mistake to make.
What, not for leaving out the solids?
Yes, you have to leave out the solids and you have to leave out the liquids. It's an easy mistake to add the solids and add the liquids, but don't. Okay. All right, how about an equilibrium expression for this reaction? Okay, this is acetic acid plus water goes to acetate ion, and this is called a hydromonium ion. So not something you need to know. I'll just put it in here anyways. This is called acetic acid plus water. Notice that one of the protons gets transferred. That's what acids do. And this becomes acetate ion. And this becomes what's called a hydromonium ion. Okay? Okay, forgetting about all those names, is this reaction at equilibrium? Yes or no? Okay, looking at those back and forth arrows, the answer is yes. And what will the equilibrium expression be? Okay, products over reactants. Are we adding water? Why is water not in here? It's a liquid. Okay, very good. Okay, water's not in here because it's a liquid.
How come in the notes, though, it includes... Oh, wait. No, it doesn't. Just kidding.
So it's H3O.
Hydromonium ion. We'll talk about that in chapter 15. Yeah, this H3O is actually the same thing as a proton, Alex. Yeah. Okay. Yes. But does it go into this expression? Yes. Why is it? It's aqueous, and aqueous goes in there. Okay. All right. I happen to know this value of K at 25 degrees. Okay, at 25 degrees, this equals. Okay, I looked it up. this equals 1.75 times 10 to the 1.74 times 10 to the minus 5. Are there any units in here? Okay, unitless, no units. 1.74 times 10 to the minus 5. So tell me, is acetic acid a weak acid or a strong acid? 1.74 times 10 to the minus 5. Okay, look at the value of this number, 1.74 times 10 to the minus 5. Weak or strong acid? Acetic acid, what do you think? Is it like hydrochloric acid, sulfuric acid, nitric acid, one of those? Is this a strong acid or a weak acid?
Weak, 'cause it doesn't.
It would be a weak acid. Okay, weak acid. This would not go very far this way. It will still give you proton. It will still give you hydromonium ion, but not a great source of protons, or not a great source of H3O+. Why is that? Okay, look at this number, 1.74 times 10 to the minus 5. What do you think about that number? Large or small? Okay, it's a small number. It's tiny. Okay, remember, if this was large, like a million or a billion or whatever, that's moving forward. If it's small, it's not moving forward as much. It's still moving forward, but not a lot. Okay? So what would we have more of, reactants or products in this equilibrium? This equilibrium reaction favors reactants, correct. All right. Right, so here are some differences between rate constant K, which was chapter 13, last chapter, and what we're studying in this chapter. Okay, so note the differences. Okay, and the similarities are that they're both quoted at a specific temperature, but other than that, they're very different. This is how fast we expect a reaction to proceed based upon zero order, first order, or second order decay. Okay, this is to what extent a reaction will go to. More products or less products. Okay, so this capital K, which is the focus of this chapter, is what the reaction favors. Okay, is the reaction going to go more towards the product side in the equilibrium balance, or is it going to go more towards the reactant side in the equilibrium balance? Okay, our last chapter was all about how fast. Okay, is it zero order decay, first order decay, second order decay? What is the half-life? Okay, that all is encompassed in rate constant. Okay? This is something totally different, equilibrium constant. Oops, I had no idea it was so blurry. Okay, I'll pause for about a minute and let our eyes acclimate to this. You should tell me when you get blurry, okay? Bad. Don't forget, this K is no units. Okay, unitless, the equilibrium constant. All right, let's do a problem here. Okay, I think this is straightforward once you know the expression. What's one important rule about this K that I don't want you to lose any points on? What does not go in here? Solids or liquids, very good. Okay. Kc and Kp for the decomposition of N2O5. All right, I'll give you this equation on the exam, so don't worry. Kp is equal to Kc times RT and that RT is raised to the power of delta N. Let's see if we can make this a little bit better. We know Kc here is concentration of products. So concentration of O2, the C stands for concentration, times the concentration of NO2. We will raise it to what power? 4 divided by, so we're balanced, right? 4, 10, yeah, we're balanced. Divided by the concentration of reactants. And what should we raise that power to? This should be raised to the 2 power. Okay. R is 0.0821. So we're without units, so I don't care about units because the whole K is without units. So we don't worry about units here. And what else can we do here? I think we'll just do, okay, we can also do this in terms of pressure. Pressure of O2 times pressure of NO2 raised to the 4th power divided by pressure of N2O5 raised to the 2nd power. Okay. Let's plug, here's what I'll do. I'm going to plug this in here. Put R in here. They're not giving us a temperature. What is delta N? That's what really I want you guys to know. Okay, how many gases in the product side? How many gases? 5. Very good. How many gases in the gases now? Gases in the reactant side? 2. So the change in the number of moles of gas is 3. The change in the number of moles of gas is 3. So let me just do a little expression here. Kp is going to be, I'll substitute Kc here. That whole thing is cubed. So if I knew the concentrations of these guys, if I knew the temperature, I can take R, which is a constant, times the temperature, cube it, multiply it by all the concentrations, and then I'll get this equilibrium expression in terms of pressure P. Right, I'll give you this equation on the quiz or on the exam. You will not get something like this on the test, but the idea is that you can interconvert between one and the other if you're dealing with gases. Okay, you can go between gases being expressed in terms of concentration or gases being expressed in terms of pressure P. Yeah, go ahead. Well, the whole thing, Michael, is unitless. K is without units. So the real units of R is 0.0821 liters times atmospheres divided by mole Kelvin. If you're doing any other problem, we would be interested in the units. The whole K is unitless, so we don't care about the units.
Okay, so I'm confused. How do you know what order to put everything in? Like, the difference between Kc and Kp. Will that be given?
C, it just stands for concentration. So you'll do products over reactants. Don't forget to raise it by the number that's used to balance it. Kp, you just put it, it's pressure. So you'll just put pressures. You can plug in the concentrations here and get Kc. You can plug in the pressures here if the problem gives you pressures and get a Kp.
Does this one give us pressures?
No, it didn't give us any pressures or any concentration. So there's no numbers in this problem. You won't see something like this in the exam. It's just how to plug things in. Okay, if I were given concentrations, I can get Kp. If I was given pressures, I can get Kp. So yeah. All right, any other questions or comments here? This is just going from one to the other. All right, now this next one has some numbers, so something probably a little bit more tangible for you guys. So let's see if we can finish this page and maybe page 8. Yeah. All right, the equilibrium concentrations for the reaction between carbon monoxide and molecular chlorine to form carbonyl chloride, that's shown here. So question for you guys, is this reaction at equilibrium? Yes, okay. And then this is an error here in my notes, so I didn't get a chance to update it, but this is the equilibrium constant. So, yeah, my notes have errors. That's just the way it is. Equilibrium constant. So.
Mine says equilibrium.
Oh, it does? Mine does it. Okay. Wonderful, good. Okay, we're dealing with equilibrium constant. Okay, Kc. Okay, so at 74 degrees, okay, this is a very specific temperature. We have concentration of all of these. So what is the formula, or what is the expression for the equilibrium constant in terms of concentration? It's products over reactants. Are we balanced? Carbon, carbon, 2 Cls, 2 Cls, 1 oxygen, 1 oxygen. Yeah. All right, so concentration of products, COCl2, divided by the concentration of reactants. Okay. Is everyone okay with that? I'm glad we're like actually just recording this, not actual camera crew. You can come in. Somebody came in just like. All right, what's the concentration of COCl2? 0.14 divided by concentration of CO, 1.2 times 10 to the minus 2. What's that? 0.012 times the concentration of Cl2, 0.054. So this happens a lot actually in colleges, just people come in and come out, especially in the bigger schools. All right, are you guys okay with this, my substitutions? All right, what's this on our calculator? $216 or something? $216.04, okay, at 74 degrees C. So question for you guys, does this favor this number, 216, does this reaction at these concentrations favor the products or the reactants? 216. Is it greater than 1? So it's going to favor the products. That's correct. Okay. It's a large number, 216, so it favors the products. All right, consider the reaction at 395 Kelvin. NH4HS solid goes to NH3 plus H2S gas. Is this reaction at equilibrium? Yes. Partial pressure ATMs is 0.265. Calculate Kp and Kc for the reaction. Let's first calculate Kp here. The P stands for pressure. It's going to be the pressure of NH3 raised to what power? Are we balanced? 4, 5. Yes, we're balanced. Okay. Pressure of NH3 times the pressure of H2S. Each raised to the 1 power divided by, do we divide it by NH4HS? No. Okay, good eye. We do not divide it. Why? How come? Okay, so it's a solid. All right, each pressure is 0.265 ATM. Okay, we don't have to worry about units. So the Kp here is going to be 0.265 times 0.265, and on my calculator I'm getting 0.0702. All right, now let's calculate Kc, because these gases can be expressed in terms of concentrations. So that equation is this. That RT is raised to the delta N. What is delta N here? Okay. We have 1 mole of gas in the product side. We have 1 mole of gas in the product side. Total of 2 minus how many gases in the reactant side? This is a solid. So how many? 0. Okay. So this is products minus reactants. All right, I'm going to try to finish this problem and then we can go here. Kp, we calculated it as 0.0702. Kc is what we're trying to solve for. R is 0.0821. As I mentioned, Michael, we don't care about units because the whole thing has no units. The temperature here is 395 Kelvin. Okay, we're going to keep this at Kelvin. And this N is squared. Okay. Delta N is 2, so delta N is equal to 2. So Kc is equal to 0.702 divided by 0.0821 times 395. Okay, that product gets squared. And what did you guys get here? See if you get what I'm getting, and that's about 6.68 times 10 to the minus 5. Okay, in terms of concentration. Both of these numbers are less than 1, and they both corroborate one another in that this equilibrium reaction favors the reactants. Okay, small number, less than 1, small number, less than 1, favors reactants. Okay, I'm going to say equilibrium favors the reactants. All right, on Wednesday's class, we'll talk about what happens when you add some reactions together, equilibrium reactions. If you add a reaction, you multiply the equilibrium constant. You flip a reaction, you take the reciprocal of the equilibrium constant. If you multiply a reaction by 2, you square the equilibrium constant. If you multiply a reaction by 3, you cube the equilibrium constant. Okay, so these are the 3 rules we'll go over on Wednesday, and then we'll also go over the Gator rule. Okay, anybody like gators? We'll go over the Gator rule as well on Wednesday. So have a good day.